What is the bisection method? It's a method for estimating roots. Estimate a root of an equation. F of x equals 0, where f is some function, some continuous function, ideally. Roots are also called zeros. I think it's weird to call them zeros, but that's something that people do, because zeros doesn't mean x equals 0. It just means it makes the function equal to 0. A starting point for the bisection method is to start with a closed and bounded interval from A to B, where you know just from looking at the graph, or maybe not even with technology, maybe you have enough familiarity with graphs that you can draw a quick sketch by hand and you could predict where f of A and f of B are going to have opposite signs. And ideally, you want this to be a small interval. What's the process? It's called bisection for a reason. In fact, before we look at the process, let's make a picture. Here's your generic function, continuous function. Crosses the x-axis right there. There's your root, or 0 of the function. As the book does, let's call it P. From looking at the picture, you decide to pick A here and B here. Maybe for sake of argument, pretend A is 1 and B is 2. Okay, I didn't have to do that. The sign of f of A is negative, and the sign of f of B is positive. They have opposite signs. By the intermediate value theorem, there's got to be a root in between. It's natural to guess halfway between A and B. Right there. As your guess. It's just a natural thing to guess. It's like, if I ask you to pick a number from 0 to 1,000 and not tell me what the number is, but when I make guesses as to what number you're thinking of, and you tell me go higher or go lower, it makes most sense for me to cut it in half and guess 500 first, right? Then you tell me go higher, and then I guess 750. And you tell me go higher, and I guess 875. Then you tell me go lower, and I guess halfway between 700 and 875. That's what we're about to do, except a smaller interval here. Let A1 be A and B1 be B. And for your first guess as an estimate for P, pick P to be the midpoint of this line segment. Halfway between A1 and B1. Average them. However, for computer programming reasons, it's better to write this average in this way, as A1 plus B1 minus A1 over 2. They are the same thing, actually. Here you're taking this, you think of this intuitively as going halfway between A1 and B1. It's their average. Here you're thinking of starting at A1 and going halfway to B1. It gets you to the same spot. And you can check algebraically by getting a common denominator of 2, that these are equal to each other. That's the better way to use if you're going to program, but we're not really focusing so much on programming in this class. If you want to program it, great. Maybe we will, but not today. You can see from the picture that the root is between A1 and P1. It's in this left interval. The next step of the algorithm is to update the values of A and B and then choose a new P. Because f of P1 and f of A1 have opposite signs, that's why you'd pick the left half of the bigger interval for your next interval to bisect. And if you bisect that interval, you'll end up with a number right about here. Call that P2. Based on a new A2, which is actually the same as the old A1, and a new B2, which is different than the old B1. The new B2 is P1. This red interval is your new interval to bisect. P2. Oh, I shouldn't have put a P there. Cross this off. I crossed that off right there. It was not equal to P. P is in green. That's the true root. It doesn't equal P1. That was confusing. P2 is the halfway point on the red interval. Yes, you could write that as A2 plus B2 over 2, but it's better for computer programming reasons to write it as A2 plus B2 minus A2 over 2. I'll make one more piece of the drawing. Now compare f of P2, or excuse me, f of A2 and f of B2, or excuse me, P2. They now have the same signs. So in this red interval, that's telling you the true root must be in the right half. Because function value at the left endpoint and function value at the midpoint have the same sign. They're both negative. You can see it visually. The root's got to be in this half. So use that half as your next interval. A3 becomes P2. This is my next interval here. The left endpoint, A3, is going to be the same as P2. And the right endpoint is going to be the same as B2. B3 equals B2. And P3 is halfway between them. It's their average, which for programming reasons you would write this way. You'd program it with that formula. Where is P3? It's right about here. That's P3. Continue the process. Question?
So when the values of the endpoints of your interval have the same sign, you know the next interval should be right?
If they have the same sign, yes. If the value of the function at the left endpoint and the midpoint have the same sign, then the next interval should be on the right.
Oh, or the left endpoint.
Yep, we focus on the left endpoint. We're always comparing the sign of the f at the midpoint with f at the left endpoint for consistency, simplicity. If they have the same sign like these do, then you pick the right interval for the next one. No, it still would be the right one. If they're both positive, the graph would be up here. And you'd still have to go to the right. Good question. If they have opposite signs, then you pick the left. So at the first step, we pick the left one, that's the red. At the second step, when we bisected the red, we pick the right one, that's the purple. Continue the process. Forever? Should we continue the process forever? No, of course not. You can't. In theory, you could keep going. In eternity, if you want, you can keep going as long as you want. But in reality here, in our finite life, we have to stop sometime. The computer has to stop, otherwise it gets into an infinite loop and starts making noise like my computer's doing right now. So you have to have a stopping condition. Now that could be just a certain number of steps. Maybe you just say, I'm going to stop after 10 steps because I just don't feel like doing it anymore. Or it could be so that the error in using your method is less than a specified number, like 10 to the negative 4 or something. 0.0001. And there is a discussion at the end of section 2.1 in the book about how to choose the number of steps to get within a specified tolerance based on a theorem, but we're not going to talk about that today. On your homework, you'll just need to apply the method. Probably the best thing to do is make a table. Well, we can mimic what the book does. Use calculator to help you, or if you want, you can program it. Make a table of values. N, A, N, B, N, P, N, F of P, N. And your quote unquote answer is the last value of P, N. Here it's kind of like they're just doing 13 steps. You won't have to do that many. Or you might say, I want to get within a certain tolerance of 0. However, that value of F is actually closest to 0. Yet we kept going. Because maybe you don't focus on the function values being closest to 0. Maybe you focus on the A's and the B's being sufficiently close. These last two numbers there are pretty close. Effectively, the theoretical error keeps getting cut in half every time you do this step because you are bisecting the interval. Okay. That's just an introduction, and you'll just need to apply the method on your homework. You can do this for any continuous function, F. Doesn't have to be a polynomial. Could be involve trigonometry or exponential functions. It could be the free fall problem that I talked about with air resistance, where there was an exponential decay. I think now would be an appropriate time to talk about, well, here the slideshow does have the method written out, not as thoroughly as the book does. The book is a little bit more precise in its pseudocode, you might say. This is a little bit vague because in like iterating, I just say update subscripts until a stopping condition is reached, and I don't say what the stopping condition is. The book's got the algorithm in there with a little bit more precision.